The research by Waasdorp et al. Investigates the enhancement of thermal mixing in turbulent bubbly flows by introducing salt. They experimentally show that salt alters the bubble coalescence properties and thermal energy spectra. With increasing salt concentration, the mean bubble diameter decreases due to inhibited coalescence, shifting the thermal energy spectrum's transition frequency from the classical 5/3 scaling to the bubble-induced 3 scaling, thereby enhancing thermal energy. The study also examines heat transport in the bubbly flow, revealing that increases in both void fraction and salinity lead to more extreme heat transport events. These findings have significant implications for industrial processes and naturally occurring processes involving turbulent mixing and multiphase flows. Turbulent flows with passive scalars, such as temperature, exhibit a 5/3 scaling in the inertial convective regime, as described by the Kolmogorov-Obakov-Corson theory. However, when bubbles are introduced into the flow, the scalar spectrum can exhibit a 3 scaling, similar to the kinetic energy spectrum of bubbly flow. This phenomenon has been observed in both experimental and DNS studies. The coalescence of bubbles can be inhibited by dissolving certain salts into the water, which affects the surface potentials and resulting changes of the Gibbs-Marangoni pressure. This effect has been observed in ocean foams and has implications for industrial applications such as froth flotation. This study investigates the transition from a single-phase 5/3 scaling to a bubble-induced 3 scaling in the thermal energy spectrum of turbulent flow. The experiment is conducted in a vertical water channel setup with a small lateral temperature gradient, allowing for heat transfer but not significant thermally induced buoyant forces. The bubble size is controlled by varying the salt type and concentration, and its influence on the transition frequency between the 2 scalings is studied. Additionally, the local heat transport properties are examined by measuring temperature and velocity simultaneously, with a focus on the effect of bubble size on local heat transfer. The paper is organized into sections, with the experimental setup and procedure described in Section 2, followed by the determination of bubble size, scalar spectra, velocity and temperature statistics, and local transport properties. This research paper explores the enhancement of thermal mixing in turbulent bubbly flow through the introduction of salt. Utilizing a water tunnel with an active grid to generate isotropic turbulence and a needle bed for bubble production, the experiment demonstrates that the addition of sodium chloride hinders bubble coalescence, resulting in smaller average bubble diameters compared to systems without electrolytes. High-speed imaging techniques were employed to study the bubbles, capturing images at mid-height of the test section. Flow velocity was measured using laser Doppler anemometry, avoiding potential issues with unwanted interactions between salt and CTA probes or probe-probe interactions. Polyamide particles were added to the water for seeding, ensuring a particle Stokes number of approximately 1.8 times 10 to the 5. Instantaneous temperature was recorded using a fast-response thermistor with a response time of 7 milliseconds and calibrated precision of 1 mK. The voltage potential of a bridge circuit, where the thermistor acts as a variable resistance, was measured with a lock-in amplifier at a sampling frequency of 13.39 kHz. The primary objective of the study is to quantify changes in mixing behavior in bubbly turbulent flows compared to single-phase flow. This is achieved by measuring the turbulent heat transport, represented as the product of horizontal velocity fluctuations and temperature fluctuations, UXT. This quantity is of interest since it appears in the balance equation of the passive scalar variance in incompressible flow, and accurate measurements could be beneficial in modeling this quantity. An ideal experimental setup involves measuring temperature and velocity simultaneously, which is challenging due to the different thermal diffusivities of each phase. However, the chosen methodologies aim to overcome these complications and provide valuable insights into enhancing thermal mixing in turbulent bubbly flow. The TMHT system setup and measurement device alignment are critical for accurate measurements. The camera and LDA transceiver are precisely aligned for this purpose. The section then presents snapshots of bubbly flow under varying conditions of void fraction and salinity. These snapshots are essential for understanding the behavior of bubbly flows in turbulent grids. In the 5th page of the research paper, The authors delve into the challenges associated with measuring thermal mixing in turbulent bubbly flow using laser Doppler anemometry, LDA, and thermistor probes. The simultaneous use of LDA and thermistor measurements can lead to laser reflection inside bubbles heating the probe, causing signal artifacts. This issue is mitigated by increasing the distance between measurement locations. To correlate the acquired signals in time, the authors employed Taylor's hypothesis, allowing them to correspond to the same location. For flow characterization, the authors assume isotropy despite the presence of a large-scale temperature gradient. They utilize the second-order structure function to estimate the energy dissipation rate, which in turn allows them to calculate the Kolmogorov length scale, viscous dissipation timescale, and Taylor microscale. The authors report the estimated values of these parameters, including the Taylor-Reynolds number, Pakelet number, and scalar Pakelet number. The authors also describe their bubble detection and characterization method, which involves imaging techniques and post-processing steps such as background subtraction, circular Huff transform, and particle tracking algorithm. This method enables them to determine bubble locations, radii, and velocities. The authors present the size distribution of bubbles as a function of void fraction and salinity, showing that increasing salinity leads to a decrease in bubble diameter. This decrease is attributed to the prevention of bubble coalescence by sodium chloride, resulting in smaller bubble diameters. The table provided details experimental parameters for various void fractions and salinity levels, including surface tension, viscosity, and density values. These parameters are crucial for understanding the behavior of fluids in the context of the research. The data is sourced from various studies, ensuring accuracy for the calculations. The table's structure allows for a clear comparison of these parameters under different conditions, which is vital for the investigation. The impact of surface tension on the gas-liquid interface is examined, as it is known to change when salt is added. The surface tension of fresh water and seawater is quantified, and the capillary number, which represents the ratio of viscous forces to surface tension forces, is calculated. The capillary number is found to be much smaller than 1, indicating that the change in surface tension due to increasing salinity cannot be the driving mechanism behind the changing bubble size. Instead, the physical destruction of bubbles by passing through the active grid and the subsequent restriction on coalescence are identified as the primary mechanisms. Temperature spectra obtained from measurements with a thermistor are presented in Figure 2, showing the spectra as a function of alpha, with a constant and zero salinity, as well as the spectra for low alpha as a function of salinity, high salinity as a function of alpha, and high alpha as a function of salinity. The results show that a 3 scaling is reached at lower void fractions for high salinity than for low salinity in the frequency range between 5 and 20 Hz. The frequency at which the transition from a 5/3 scaling to a 3 scaling occurs is found to be dependent on the void fraction. To investigate this transition frequency, a parametrization is applied, given by equation 4.1, which describes the power spectral density of the temperature fluctuations. The fit is applied in the frequency range from 1 to 20 Hz, and an example of this fit in the transition region is shown in Figure 10 in Appendix B. The transition frequency is extracted as a function of void fraction and salinity, and is shown in Figure 3, which reveals two notable trends. The transition frequency decreases with increasing void fraction, and the transition frequency increases with increasing salinity. Investigating the impact of salinity and void fractions on thermal spectra in two-phase flows reveals significant influences of bubble presence on thermal spectra, particularly in the low-frequency region. This leads to a deviation from the classic 5/3 scaling, attributed to bubble-induced 3 scaling caused by wakes generated by bubbles. Normalized thermal spectra, plotted as a function of salinity and void fractions, illustrate this deviation. At low salinity, the thermal spectrum exhibits a clear 5/3 scaling at low frequencies, deviating towards 3 scaling at higher frequencies. In contrast, high salinity displays a more pronounced 3 scaling across all frequencies. Single-phase flow, however, shows no deviation from the 5/3 scaling. High void fractions display a distinct 3 scaling, similar to the high salinity case. The observed deviation is linked to changing bubble size with salinity and void fraction. The transition frequency, marking the shift between the 5/3 and 3 scalings, increases with increasing salinity, correlating with a decrease in bubble diameter. This indicates that bubble size and its resulting wake play a crucial role in determining the transition frequency and thus the thermal spectra. These findings contribute to understanding how salinity and void fractions affect thermal spectra in two-phase flows, highlighting the complex interplay between these parameters and bubble dynamics. The study underscores the importance of considering the impact of bubble wakes on the energy cascade in such systems. The authors investigate the enhancement of thermal mixing in turbulent bubbly flow by adding salt. Figure 3 presents the transition frequency from a 5/3 scaling to a 3 scaling as a function of void fraction alpha and salinity S, compared to previous results from Dung et al. 2023. The error bars ensure good visualization with the log scale on the vertical axis. The authors then examine the individual velocity and temperature distributions. Using laser Doppler anemometry, LDA, they acquire 10⁵ data points covering a duration of 20 minutes. Figure 4 displays probability distributions of the velocity in the horizontal direction. Figures 4a, 4b, and 4c show the horizontal velocity distribution as a function of the void fraction, salinity, and for single phase and high void fraction, respectively. The distributions demonstrate agreement with earlier results for zero salinity, as reported by Dung, 2021. With increasing void fraction, the distribution narrows around the mean and increases in the tails, highlighting the increased occurrence of extreme events and mixing in the liquid due to the increasing amount of energy injected by the bubbles. Figure 4c reveals a similar increase in intermittency due to the presence of bubbles, which is more pronounced for higher salinity. This change is attributed to the changing bubble size and aspect ratio. The authors also discuss the temperature distributions, which were measured for both increasing void fraction and increasing salinity. In a water tunnel setup, this study investigates the effects of varying salinity and void fraction on the characteristics of turbulent flows. By measuring the probability distribution function of horizontal velocity and temperature, the research reveals that, for single-phase flows, temperature distribution remains relatively constant with changing salinity. However, when the void fraction is high, the temperature distribution exhibits a more defined trend with increasing salinity, characterized by wider tails and a skewed distribution. This skewness is attributed to the shift in equilibrium location due to bubble properties. The study also examines the impact of bubble size on flow fluctuations. Larger bubbles produce larger fluctuations but fewer in number, whereas smaller bubbles generate more frequent agitations due to their higher numbers for a given gas volume. This phenomenon explains the increased intermittency observed with both higher salinity and void fraction, as these conditions lead to a greater number of bubbles present. The research highlights the complex interplay between salinity, void fraction, and bubble characteristics in turbulent flows, providing insights into the intricate dynamics governing such systems. By elucidating the intricate relationships between these variables, this study contributes to a deeper understanding of the underlying mechanisms driving turbulent flows in water tunnel setups. The authors investigate the effect of adding salt to enhance thermal mixing in turbulent bubbly flow. Figure 5 presents the probability density function of the standardized temperature, T, as a function of salinity, revealing a broader temperature distribution with increased salinity, implying enhanced thermal mixing. Figure 6 illustrates the normalized variance of temperature and velocity as a function of void fraction and salinity. Although the trends observed for zero salinity water are maintained with increasing salinity, a clear monotonic relationship with salinity is absent. The decrease in Weber number with added salinity suggests that the salt reduces the agitation created by the bubbles, influenced by factors such as velocity, shape, and diameter. The paper then focuses on turbulent heat transport, emphasizing its dependence on the scalar flux and its distribution. Figure 7 displays the distributions of the measured heat flux, defined as the product of the fluctuations of horizontal velocity and temperature. The results demonstrate that the tails of the distributions increase with both void fraction and salinity, indicating enhanced thermal mixing. Figures 7a, 7b, and 7c present the heat flux distributions for zero salinity, high salinity, and high void fraction, respectively, showcasing similar trends. The addition of salt leads to increased thermal mixing, as evidenced by the broader temperature distributions and increased heat flux. However, the complex interplay of factors influencing the Weber number and turbulent heat transport necessitates further investigation to fully understand the underlying mechanisms. The authors examine the impact of bubble size and shape on the mixing properties of a turbulent flow, finding that reducing bubble size and altering bubble shape increase the intermittency of the scalar field, leading to enhanced mixing. This supports Villermo's definition of mixing as stretching enhanced diffusion. In their experiment, a small imposed temperature gradient allows the temperature to act as a passive scalar, and the authors observe an increase in intermittency, where small parcels of hot or cold fluid are moved around the fluid field, leading to enhanced mixing. The standard deviations of the measured heat flux signals, shown in Figure 8a and b, increase with increasing void fraction and salinity, confirming previous findings. To gain insight into the measured heat flux, the authors employ the passive scalar variance balance equation for incompressible Navier-Stokes flow, assuming a statistically stationary and unidirectional flow, a mean temperature gradient in the horizontal direction, and negligible diffusive variance flux. Using a boundary layer approximation, the passive scalar variance equation is written as equation 6.1, which includes the scalar fluctuation dissipation rate ETH. The authors question whether the heat flux can be accurately modeled using the eddy diffusivity hypothesis, as in previous works, where the heat flux and variance flux are written as equations 6.2 and 6.3, respectively. However, they note that their measurements are not suitable for approximating the diffusivities kappa t, xx and kxx, due to the mean value being close to zero and the lack of correlation between velocity and temperature measurements. Figures 7a through 7c display the heat flux as functions of void fraction and salinity, but the authors emphasize that their measurements are not appropriate for modeling the diffusivities. The study on enhancing thermal mixing in turbulent bubbly flow by adding salt presents the probability density functions, PDFs, of heat flux as a function of void fraction and salinity. Figure 7 illustrates the PDFs for varying void fractions at different salinity levels, while Figure 8 shows the standard deviation of heat transport fluctuations as a function of both salinity and void fraction. In Figure 7, the addition of salt significantly alters the distribution of heat fluxes, particularly for higher void fractions. For instance, when the salinity is increased from 0% to 2%, the PDFs shift towards higher heat flux values, indicating enhanced thermal mixing. This trend continues with further increases in salinity, demonstrating the positive impact of salt on heat transfer in turbulent bubbly flow. Figure 8 provides a more detailed analysis of the heat transport fluctuations. The standard deviation of these fluctuations is plotted against both salinity and void fraction. It is evident that the standard deviation increases with increasing salinity, suggesting greater variability in heat transport. However, this increase is more pronounced at higher void fractions. Interestingly, the single-phase case, which does not involve any bubbles, shows relatively constant standard deviation regardless of salinity. These findings underscore the importance of considering the interplay between salinity and void fraction in optimizing thermal mixing in turbulent bubbly flow. The addition of salt can significantly enhance heat transfer, but its effect varies depending on the presence and concentration of bubbles. This research has implications for various industrial processes, such as chemical engineering, where efficient heat transfer is crucial. Turbulent bubbly water flow with a thermal mixing layer is examined to elucidate the effects of sodium chloride, on various aspects of this phenomenon. The study reveals an inverse relationship between void fraction and transition frequency between the 5/3 scaling and the 3 scaling in temperature spectra, whereas an increase in salinity leads to an increase in transition frequency. This shift is attributed to changes in bubble properties resulting from varying void fraction and salinity. Furthermore, the investigation explores transverse heat transfer in thermal turbulent bubbly flow, finding that the mean of the product of velocity and temperature fluctuations remains unchanged and uncorrelated in the experiments. However, a monotonic increase in the standard deviation of this quantity is observed with increasing void fraction and salinity, but only when bubbles are injected. This suggests that the presence of bubbles enhances mixing properties, with bubble size being a crucial parameter for the change in mixing properties. These findings contribute to a deeper understanding of the complex interactions between bubble properties, void fraction, and salinity in turbulent bubbly water flow with a thermal mixing layer. The research was supported by the Netherlands Centre for Multiscale Catalytic Energy Conversion, MCEC, an NWO gravitation program funded by the Ministry of Education, Culture and Science of the Government of the Netherlands. In the realm of turbulent bubbly flow, enhancing thermal mixing is a crucial endeavor. This page delves into the impact of adding salt to achieve this goal. The circular Huff transform is employed on experimental images to detect bubbles, an approach that has its limitations, particularly in identifying non-circular bubbles at lower salinities and void fractions. A manual investigation of bubble aspect ratios was also conducted, yielding results comparable to those obtained from the circular Huff transform. It is essential to consider the limitations of detection methods when interpreting bubble size distributions, as they can significantly influence our understanding of these phenomena. Continuing the exploration of bubble-induced turbulence in a low-sheared inhomogeneous bubble column, this study delves into the accuracy of the fit in thermal spectra using the generalized Batchelor parametrization, as expressed in equation 4.1. Two examples are presented for low and high void fractions with a salinity S equals 2%, showcasing the transition from 5/3 to 3 scaling in the frequency range. The Batchelor fit, applied between 1 Hz and 20 Hz, demonstrates a good agreement with the data. This suggests that the proposed parametrization can effectively capture the characteristics of the temperature spectra in the specified frequency range. Enhancing thermal mixing in turbulent bubbly flows is crucial for various industrial applications. Previous studies have investigated the gradient diffusion hypothesis and passive scalar transport in turbulent flows, laying the foundation for understanding thermal mixing. However, the effects of electrolytes on bubble coalescence remain largely unexplored. Research by Craig et al. And Dignan has shown that electrolytes can significantly influence bubble coalescence, with important implications for thermal mixing. The concept of bubble-induced scaling in thermal spectra has been introduced by Dung et al. And Waasdorp et al., highlighting the significance of bubble dynamics in shaping thermal spectra. Moreover, Dignan's work has emphasized the critical role of surface potential in ion-specific bubble coalescence inhibition, which can further impact thermal mixing. To advance our understanding of thermal mixing in turbulent bubbly flows, controlled experiments are essential. The Twente mass and heat transfer water tunnel provides an ideal platform for investigating turbulent multiphase channel flow with heat and mass transfer. Future research should focus on this complex phenomenon, leveraging the insights from previous studies to develop a deeper understanding of the underlying mechanisms and their interactions. In turbulent flows, understanding the temperature field structure is crucial. Obukov's work has been instrumental in shaping our knowledge of this complex phenomenon. Building on this foundation, research has shifted focus to the impact of gas bubbles on turbulent flows. Experiments by Poort and Beschouvel, as well as Pope's comprehensive book, have provided valuable insights into this area. Recent studies have delved deeper into the role of bubbles in turbulent flows. Prakash et al. And Renson et al. Have investigated the effects of bubbles on turbulence, revealing significant modifications to energy spectra. Ribu et al. Have further explored these interactions, highlighting the complex interplay between bubble dynamics and turbulent flow structures. These findings have significant implications for our understanding of turbulent flows and their applications in various fields, including engineering and environmental science. By elucidating the mechanisms underlying bubble turbulence interactions, researchers can develop more accurate models and improve predictive capabilities. The intricate relationships between bubble size, distribution, and turbulent flow characteristics are critical in determining the overall impact of bubbles on energy spectra. Future research directions include exploring the effects of varying bubble sizes and distributions on turbulent flows, as well as investigating the role of bubbles in more complex flow geometries.